All right, hey everybody, happy Monday, and we're on to section 1.4 today, properties from algebra. Now we're going to spend probably all week on section 1.4, so it's kind of a big one because we've finally gotten to this here. And you've noticed this here, and I had a slide very similar to this recently. Here in all caps here, I have the word facts. Okay, so what this week's going to be all about is just very introductory, the basics about how to prove facts. Now, you remember towards the beginning of the year, we studied these things called if-then statements. If-then statements, if you put some together, right, you put multiple if-then statements together, you can establish facts in the world, and that is super, super important. It was important a long time ago. It's important now, okay? So we're looking at a few key people from history, including modern-day history right here. But for instance, on the left side here is the original fact finder. We have ourselves Euclid. Now, remember, Euclid kind of laid out geometry for us, but beyond that, he kind of put together kind of the most logical way of thinking that humankind had ever believed ever really existed here. Okay, so he sort of was a big part of developing, along with Aristotle and the early Greeks, maybe not along with them, but within 100 years or two of them, deductive reasoning. Okay? So if you remember the three things that are in deductive reasoning, the three things in order to prove a fact requires what? Well, maybe think about what we've been doing the past few sections. What have been the big things? What have been kind of dumped on top of you guys, the first three sections of geometry? You've gotten a lot of what? We got a lot of definitions, that's for sure, right? We've defined a whole bunch of terms for you, classify what things are and differentiate what those things are. Secondly, what was it? So remember, there's definitions, rules, and finally facts, okay? So we got some rules, and those are called postulates, right? They were called postulates in Euclid's book right there. So Euclid did a lot of work with how do you actually get a fact. And you guys watched a video over the weekend where this gentleman right here talk about how his sort of love of Euclid and his work that he did and how he used to do geometry just to kind of fine tune his mind. And of course, facts were incredibly important to this person over here, Abraham Lincoln, even before he was president, before all the stuff he did. But the stuff that actually Euclid wrote influenced some of the decisions he made as president. In fact, we'll watch a video pretty soon about that here. But of course, as a lawyer, right, as you saw in your video, he wanted to prove things beyond a reasonable doubt. What exactly does that entail? How do you prove things as perfectly as possible? Well, Euclid in geometry showed him kind of a way, a method, and that's what we're going to kind of talk about today. In the middle, of course, we have here Dr. Fauci. A reminder on that one there, facts are still super, super important right now to science and health and politics and all that good stuff here. So when you're somebody who trusts science and realizes facts come from somewhere, perhaps you'll say something a little more rational, like maybe we won't have a vaccine until like midway through next year or so, rather than it'll be coming on election day, right? Or before election day. You might have heard somebody else make up a fact and say that recently in the news. So anyways, facts are super important. We're going to get into facts today. And what we're going to talk about in terms of facts today are going to be just stuff you've already done before. Facts in algebra, right? Facts in algebra. Because you actually, believe it or not, can prove facts in algebra. So that's what this whole class is about today, is about taking the stuff you've done in algebra before and realizing that making a statement such as this, and we'll talk about this one in a second, is something that you could prove as a fact right here. Okay, so for instance, this here, we have an equation. Say we have an equation here, 4x plus 2 equals 20, right? If we have this equation, 4x plus 2 equals 20, a fact that would follow from this statement right here is that x must equal 6, must equal 6. That's a fact, okay? We're going to prove that one today. I'm going to talk about some of the various things we do when proving things, and that's going to help us when we get into geometry a little bit later. Some thought questions right here. How do you know that it's this for sure? How do you solve it? Stuff like that, okay? So obviously you might be thinking, if I have this equation right here, and I know that this is my answer, right? I know that this is a fact. I can be sure that my fact is true, right? If 4x plus 2 equals 20, then x equals 6. I would know it's true because I could plug in, right? I could plug in. 4 times 6 is 24. Wait, this is wrong. 4 times 6 is 24. Oh, man, what happened here? Should have been 3. Oh. All right, guys, we're back here. I fixed this slide. It was right in the rest of the assignment here. So anyways, now we have an actual fact here, and that is if, listen, that's an if-then statement. If 3x plus 2 equals 20, then x equals 6. Now it's a fact, right? 3 times 6 is 18 plus 2 equals 20. So obviously it's a fact, right, because we know it's true, but we also would know it's a fact because we can solve this using rules of mathematics. By using definitions and rules, That leads us to facts here, okay? So let me just show you what I'm talking about right here, because, guys, you've been able to prove things and actually get facts done in algebra beforehand, and kind of reasoning through it here. So you're actually going to do a little proof, right? Prove this as a fact right here. So in math, facts are done by writing a proof. And here's an example of a proof right here. So if we have this statement right here, so proofs are written in if-then statements. They don't always look like this. We'll get to it later, what they also look like in the future. But the idea is here is that if we have this, okay, this is what's given to us right here. This is our given. So this is something called a given premise, an original fact at the beginning. It's just the premise of the problem, right? The situation we find ourselves in. And we got 3x plus 2 equals 20. So if 3x plus 2 equals 20, then we can work on solving this here. So then we can actually make a statement. And I know eventually we'll get to x equals 6, but question, how actually would you solve this? Just look at this for a second. How would I actually solve this here? Well, what I would do, and I think what most of you would do, is we got to get rid of that positive 2 right there. So I can subtract 2 from both sides of the equal sign. If I subtract 2 from both sides of the equal sign. So what I can actually conclude is if I knew that 3x plus 2 equals 20, then I would also know that 3x equals 18. You get the idea. You subtract 2 from each side of the equal sign, equality is preserved. And we know that this is actually then a true statement. So in math, we can write an if-then statement like that. And the reason why we can actually write an if-then statement like this, right? If 3x plus 2 equals 20, then 3x equals 18, is because we have a rule to justify that. Because what did we do? Well, we subtracted 2 from both sides of the equation because we minus 2 from both sides of equals. Therefore, right, once we have this, and now we have 3x equals 18, what can we do to 3x equals 18 to actually get to what we're trying to prove, that x equals 6? What's our final solving step there? Somebody raises their hand, they say this, right? Oh, divide both sides by 3. You got the right idea. You're so good, right? So we can divide this by 3, divide this by 3, and we can get another true statement down here that x would have to equal 6 because we divided both sides of equal by 3. And that, of course, is a rule. If you divide one side of an equation by something, you divide the other side of the equation by the same thing, and equality is preserved. This was a rule up here, a justification that if you subtract 2 from one side of the equal sign, you got to subtract 2 from the other side, and equality is preserved. So here we've actually proven a fact, right? We've proven a fact that if 3x plus 2 equals 20, then, right, we're going to be able to prove that x equals 6. It will follow from that. So this is an example of a proof, right? This is our first algebraic proof. This is similar to the one that you did with the squares, right? The very first real week of class or so, we did the thing with squares and you proved the thing about the area of square A. Remember the little one right there? You strung together if-then statements, okay? So proofs and writing a proof sort of hinges on using if-then statements. And it also relies upon using definitions and rules, of course, to justify your if-then statements and why they're actually true here, okay? So in your section right here, this is in section 1.4, you have some things to memorize, some things to know right here, and they are right here. So these are called the properties of equality. It's kind of the main thing I want to get out of Monday. And then again, we'll keep building on this throughout the week. But instead of writing things like subtract 2 from both sides of equals or divide both sides by 3, like we did in the last proof we just did, this year we're going to be using the official algebraic rules, right? Official algebraic rules. These are called properties of algebra from algebra on page 17. And they're as follows right here. These are sort of the most important ones. Although on page 17, there are a few more. Okay, there are a few more. Note that you should take notes about what each of these properties mean. So let me just go to the textbook for a second. Oops. Let me go to the textbook. And on page 17, so here is the section 1.4, and here's page 17. So here's probably right here. This is the properties of equality, the properties from algebra. You'll have to know this here. I'll be using these all year long. So definitely when you read this, right, read this later. And I'll be going through most of these right now, actually. Maybe take notes and hear what I'm saying about these. So things that we'll be using here: addition, subtraction, property of equality. We'll talk about exactly what that means. And there's some words down here you might not know. Here, like reflexive, transitive, what the heck does that mean? And then on Wednesday, algebra and geometry, these will just be used in geometry. We'll talk about that on Wednesday, okay? Getting back to our presentation right here is, let's talk about them right now. We got ourselves our rules that are used to prove facts in algebra here. So these are all statements here that you know from Algebra 1. At least the first 4 I'll go through. The last 3 probably you don't know from Algebra 1, but they're the justification for why we're allowed to solve equations, why we're allowed to rewrite equations. And these aren't proven facts, right? These are rules that are used. So you can think of these as kind of rules. That's something that early mathematicians got together and said, we're doing these things to these equations, and it just makes sense, right? It's not something that's proven. It's just something that's really obvious. For instance, the addition property of equality, or abbreviated plus prop and equals, because you'll be writing this quite a bit, so you're welcome to abbreviate it like that. This was a plus over here. This one says if A equals B, so it's just kind of using variables for this one here. If A equals B and C equals D, then A plus C would have to equal B plus D. Well, what the heck does that mean? What is actually happening right here? What's our given premise here? If A equals B and C equals D, then we can make the conclusion that A plus C would have to equal B plus D. What changed here? What's happening here? What's being said here? Well, it looks like to me here, right? The idea is that if we have 2 equal values, another 2 equal values, we can take this equal value, right? And we can add it to one side of the equation here, as long as we take the other equal value and add it to the opposite side of the equation right here. So here I put plus C, and here I'm putting plus D. And notice here, if I do A plus C, I get this, A plus C. So now the left sides equal the right side here. So kind of on this one here, you can summarize in your notes, right? Adding the equal things to both sides of another equation, right? Which means equal things too, preserves equality, right? We'll keep equality right here. So we know if we add equal things to both sides of an equation, the equation is still balanced, it's still an equal equation. And we also know that we can subtract equal things from both sides of the equation here. So looking at this down here, right, I have this here in my given premise, if A equals B and C equals D, right? C equals D, those are the same things, right? They're the same thing as one another. So if I take this equation and I take away C from one side, right, lower that equation by the amount of C, right, whatever C represents, and then I'd have to lower this one by the amount that D represents right here, so I could subtract D from this side, and where would my scale be? Where would my balance be, my equation be? It'd be equal to each other. Equality is preserved here, okay? So I can take away equal values from both sides of an equation, and my equation is still balanced, is still the same here. Subtract 2 from both sides like we did in the last one, you're going to get an equation, right? If you started with an equation, you subtract 2 from both sides, you end with an equation afterwards here. So this is called the subtraction property of equality. We'll be using that to justify and get us some new facts later this year. In yellow here is just kind of shorthand, it's the way it's summarized kind of in your notes. Addition property of equality, here's how I'd word it. If something is equal to another thing, then those equal things can be added to opposite sides of an equation. That's allowed, and then what I usually say out loud is that equality is still preserved, right? You started with equal statements, you added both sides, right? 2 equal things here, and you ended up with both sides still being equal at the end. So same thing too with subtracting. If something is equal to another thing, then those equal things can be subtracted from opposite sides of another equation, right? And that equation would still result in being an equation at the end of the day. All right, so obviously if you can do this with addition and subtraction, you're also going to be able to do it with multiplication and division. So a fancier name than you're probably used to in algebra used to be like, you know, hey, do one thing to one side of an equation, you got to do the same thing to the other. We're still going to talk about the operations here, right, that you're going to be doing. These 4, the core 4 math operations, you can do them to both sides here. So here we have a statement here. If we have a statement, say it's like, well, if let's just let like A be 7 or something. Let's let A be 7. Oops, I'm having trouble writing on this here. 7. And let's let B be 7. Okay, right? A equals B. Say they're both 7 here. And then here, if I have C, so C kind of is another variable, right? It would represent some unknown constant, right? A constant here. If I multiply the left side by C and the right side by C, I would get a true statement right here. I get 7C equals 7C, right? Because A equaled B, right? So I just get C times a value here times C times the same value over here, or an equal value over here, and equality is preserved, okay? So we're allowed to multiply both sides by the same thing, and the result is an equation here. Okay, same thing's gonna be true for equality, right? For division, right? We have a division property of equality here. So if we have 2 values, and we divide one by like 4 or something like that, then we divide the other side by 4, right? The result is you're still gonna have an equal equation, right, at the end of the day here. Okay, so same comment right here. We have this whole thing about C not equaling 0, and quick question for you guys. If we had two equal values and we tried to divide both sides by 0, what would happen? Well, I don't know. It's undefined, okay, undefined. So remember from Algebra 1, that might have come up a few times. If you can't, you're not allowed to divide anything by 0, right? Because that just doesn't make any sense, right? That's not something that's actually been defined, right? There's no definition for it. Mathematicians haven't agreed to it, so therefore we can't build rules off it. But anyways, if you want to divide both sides by 5, good to go. You're good to go. Divide both sides by length AB in geometry. Ooh, that's division property of equality. So then you're good to go there. Okie dokie. So anyways, here's how I put this in your notes to kind of make sure that you have it there and you remember what it is. So multiplication property of equality, I would still write the whole thing out, right? If A equals B, then AC equals BC, right? You probably know this. Probably old hat for you guys here. But I'd write if something is equal to another thing, then those equal things can be multiplied to opposite sides of an equation. Same thing with the division property. If one thing is equal to another thing, then you can divide both sides by the same thing, and you're going to get an equal result. All right, keep it moving on here. So these are now, so God, there's seven of these today, 7 rules that I want to introduce to you. And then actually after that, I'm going to go through some problems. I'm going to show you how we're going to use these things to prove more algebraic facts, right? Algebraic facts, which is really just solving an equation, but actually proving that that equation is true without having to go back and plug in. Anyways, we'll see to it. We'll get to in a second. So there are 3 more, again, 3 more down here that I'm going to talk about. I'm going to talk about this one. I'm going to skip over symmetric, but I'm going to talk about transitive here. So here are some more rules right here. We got the transitive property of equality. If A equals B and B equals C, then A equals C. Okay, and then A equals C. This one's kind of a bit wordy. Let me actually make it so I can write on this. And I can write on it now. So this one here, first of all, actually, my hints here with when you use the transitive property is to ask how many different variables are being talked about in this one. How many different things are being talked about here? We got variable A, we got variable B, and then B's over here, and we got variable C. So 3 things are being talked about here, right? 3 things. What does transitive start with? TR, right? TR. What kind of other things what other words start with TR? Think about geometry. What's something that starts with TR? Triangle, triangle. So TR here is going to allow you to remember that 3, right? The number 3, TR, transitive, deals with 3 different statements, right? 3 different statements that are actually all the same, okay? A little bit confusing, but let me show you what I'm trying to talk about here. If A equals B, okay, right? If A equals B, so here is kind of like expression 1, and it's equal to another expression, expression 2. And then here we have C again. Sorry, B over here again. So, and then we have B again over here. So here, the expression 2 is in a different equation, okay? There's expression 2 again here, and it's equal to a third equation, okay? If one thing is equal to a second thing, and then that second thing is equal to a third thing, what's the conclusion we can make? What's the rule we can set up here about this? So we know that this is our given premise that we know that 1 is equal to 2 and 2 is equal to 3. What can we conclude about 1 and 3? Well, 1 and 3 would have to be equal to each other, right? Equal to each other, because what are they both equal? Well, 1 equals 2, 2 equals 3. So if 1's the same as 2, 2's the same as 3, then that means all 3 of them are the same. Okay? So with the transitive property of equality, you're going to want to look for 3 things and really like 2 equations, right? 3 things being mentioned. That's the way that I really call it out of seeing transitive right here. And we'll summarize what it means with words in a second. Reflexive property of equality, this one's actually pretty important and comes up a lot, but it's one of the easiest reasons you'll have to remember for the whole year. So, or rules you have to remember the whole year. So reflexive property of equality, A equals A. What do you think that one means? Well, that just means if we have 5x, for instance, let's say A is 5x right here, what can we say about 5x? It equals 5x. It equals itself, okay? It equals itself. 7 equals 7. -7 equals -7. The absolute value of -40 equals the absolute value of -40, right? Anything is equal to itself, and that is a rule, right? That is a rule. Finally, we have the substitution property of equality. You guys should have studied substitution when you did systems last year, so you have a sense of kind of what that is. But this says here, if A equals B, then either A or B may be substituted in the other for the other in any equation or inequality. Okay, maybe I need to give you an example of that one here. So if A equals B, And then we have some other equations. So I'm going to put an and here. And let's say that 2b equals y. What's a conclusion we can make? What's something that we can do? What's something that we can change around, or a conclusion we can make now? If a equals b and 2b equals y, how can I rewrite? Because a lot of times in math, you just want to rewrite it. So what could my then statement be? Then what? What's the conclusion I can make? Well, I know that 2b equals y, because that's in the original statement here. But a also equals b. Then I can do this. I can do 2a is also equal to y. Right? And maybe I know what A is. Maybe I don't know what B is yet, and it's more useful to me to substitute this in. I wrote here 2A is equal to Y. So basically, it's just a way of substituting one equal value, right, in for the thing that it's equal to into another equation here. So what we're doing is we're taking this because it equals B and putting it in for B right here. Okay, so you should have practiced substitution a bit last semester, and it'll be a rule that we'll follow this year when we're proving things here. And here's how we kind of summarize it down here. It's transitive property of equality. Remember, that deals with how many different expressions? 3. And 2 of them, if 2 of them are equal to the same thing, then those 2 things are equal to each other. If 2 things are each equal to the same thing, then those 2 things are equal to each other. Look at the picture I put up there. That guy should look familiar at this point in time. Who is that guy? Ooh, he might have something to do with the transitive property. Moving on, we have the reflexive property of equality. I'm just teasing that for the future. And then so I would summarize in your notes, anything is equal to itself. And then finally, right, substitution property of equality. This will be a little confusing, right, when you use substitution this year. So we'll definitely have to practice this and practice transitive, because actually they're kind of similar. But anyways, this is what I was trying to show you earlier in the last one, right? We could take x equaling 2, right, x equaling 2, and put it in for x here, for instance, to an equation. Remember, you had to use substitution for this in algebra. You substitute x equals this, and we also know that 3x plus 2 equals y. So we can substitute 2 in for x, and that would help us solve for y, right? We would then later use just multiplication and addition to determine that y equals 8 in the statement. Okay, so here's just a quick example of what the substitution property of equality is here. And then I'm skipping over the slide. I don't know why that's there. I don't know what that's let's keep going. Let's prove this as a fact. Given this, prove this. Okay. Oh, this is the one we did already. Okay, this is the one we did already. So this is back on here that because now we have, right, you probably guessed why, because we had just talked about the rules, the official rules that help us prove facts in math. Okay, so we're going to use those official rules. So think back. What are the rules that I just told you guys? Just think back for a second. Addition property of equality, subtraction property of equality, multiplication property of equality, division property of equality. What else? Transitive property of equality. What's the one where something's equal to itself? Reflexive. Nice. Reflexive property of equality. And finally, the what property of equality? Substitution property of equality. Okay. So we want to use those rules, official rules, but we're also going to write it slightly different. The way that your book proves things is actually going to be on the slide after this. So I might actually just skip over this real quick, but I think I'm not going to say this actually be pretty quick, so we can do it really quickly because we can slide it here. So let me just rewrite the proof to show you what a slightly better proof would be, rather than writing the whole subtract 2 from both sides or minus 2 from both sides. So anyways, let's just see what we're talking about here. So anyways, if we have this, okay, remember we wrote this in here. So if we're given this, we're trying to prove this. So if 3x plus 2 equals 20, then what was the second thing we said? We said that if we're trying to prove this, we're trying to simplify and solve this, what would we have to do to both sides? We'd have to subtract 2 from both sides. So this would be the next thing I would write, is that if I know this, 3x plus 2 equals 20, and then I would know that 3x equals 18. Okay, then I would know that. And the reason why I know that, because, well, what did you do to both sides? I subtracted 2 from both sides. But what's the reason? What's the real justification? So after the because is where you put your justification. Subtracting 2 from both sides of an equation. What's the official algebra name? I just told it to you guys. Subtraction property of equality, okay? Because of the subtraction property of equality. Therefore, right, we're then able to conclude that x equals 6 because we divided both sides by 3, okay, right? If I divide 3x by 3, I get x. Divide 18 by 3, I get 6. And then this is an equal sign here. Equality is preserved because division property of equality, a rule tells us that if we divide both sides by the same thing, we preserve equality, and we're good to go. We've proven this as a fact. 3x plus 2 equals 20, therefore x equals 6. So I did it again with the reasons, but now this is what I was talking about a second ago. I forgot that I did that here. We're going to do this one last time. So we're actually going to prove this fact a third time right here because I want you to see how your book has you write out these proofs here, okay, about proving. We're just doing algebra today, but these are how you're going to write geometry proofs and find facts in geometry is by doing something like this. And this is called a two-column proof, Get used to them. They're here to stay. In order to save you from writing so many words like if, then, because, therefore so many times, because this was something that came up and a few people said like in their if, then statements assignment, man, it was fun. I liked figuring out the areas of the squares, but it was too much writing. Right? It was way too much writing. So you probably guessed it. Mathematicians, they don't like to write a lot of words, right? They don't if they don't have to, especially if you have so many if-then statements in geometry. What we want to do is we want to just assume it says if here, assume that says then here, or because here. Okay, so I'm going to explain where the words if-then might come in if you write a proof out like this here. So what we're going to do is we're going to write the same proof. If 3x plus 2 equals 20, then x, we're trying to get to prove that x equals 6. This time we're going to do it in something called the two-column form, and that's what's here. On the left column, what you see in the left column, these are called statements, okay? Your math statements go on the left side, and then on the right side, reasons, these are where your justifications go, okay? So think about it. What were the justifications in the written proof we just did with the if-thens there? What kind of justifications were there? Well, like subtraction property of equality or multiplication property of equality, okay? We need to just do it because I think just doing a bunch of examples is the way you're going to learn. I realize I'm going kind of fast in this, but I think if I can get to examples and you can stay with them, you're going to be fine in the homework and really just start to pick this up, which is the important thing here. Okie dokie. So if we pretend we haven't proven these things yet, and you're now doing it in this form, this two-column form. First time you're going to see this, so it might be kind of confusing. It says here, we got to prove if 3x plus 2 equals 20, then we need to determine that x must equal 6 here, okay? So I've rewritten this as what's given to us is that 3x plus 2 equals 20. That's our given, right? If we have this, then what we got to prove is this, x equals 6 here. So remember, what appears after the if is called the hypothesis in if-then statements. So that's what we start with. And then the thing that shows after then is called the conclusion. That's what we need to get to conclude. And we need to show all the steps and justifications from there. Okay? So step one, we got to start with what our hypothesis is. We got to start with what is given to us. Okay? So what I'm going to do is I'm going to take that as my first statement. Statements, the statement side is where your math goes. Your reason side is where your justification goes, or where the rules you're using, or definitions you're using, or already proven facts will go over there, okay? You'll see what I'm meaning later, right, when we get into this more deeply. Okay, so the reason for this on the right side here, the reason why I know that 3x plus 2 equals 20 is, well, that just didn't magically happen. I don't know that through magic. I know that because the problem gave that to us. This is given to us. This is our given problem, okay? So first step on these two-column proofs, listen to me real carefully. First step on maybe 70% of the proofs you'll do this year, the first reason you're going to see is given, because you're just going to copy down the given that's written there, okay? Both sides. What do I do? If I have to solve this, what do I do to both sides? Well, I got to subtract 2 from both sides. So I'm actually going to put this over here for a reason. And we got here, subtract 2 from both sides. I would get 3x equals 18 right here. And we subtracted 2 from both sides. So that's the subtraction property of equality. We'll put that one down right there. Next step. So actually, I don't need 5 steps for this one. I'm just going to need 3. I would go from 3x equals 18 to x equals 6, right? What did I do to both sides of the equation? I divided both sides of the equation. And we got it. We're good to go. We have this proven. I did that quickly. You're going to get 2 more examples, and then we'll wrap it up, okay? So, we just need to get through examples. Hopefully, you watch them, and you ask questions, and you practice this, right? We'll learn by doing. So anyways, another thing I want to put down here, definition, is what we just did right here, right? This is the 3rd time we've done it, but now we've done it in a 2-column form. We wrote a proof, okay? So a proof, what a proof is a formal series of statements showing that if one thing is true, okay, one thing is true, then something else necessarily follows from it. There's another fact there, right? If we know something is true, if we start with something being true, we can then show something else is true. And if we do that through a formal series of statements, that is called a proof here. So real quick, just to remind us here, this is what we started with. So here, formal series of statements showing the one thing is true. Okay, so here, this is true. This is given to us, this is true. This is our true. All right, true here. And it's true because this is our given premise, okay? Our given premise. You might hear me call this the given premise, or you might hear me call this the hypothesis, because the thing that shows up after the if here, right? If 3x plus 2 equals 20, That's called the hypothesis, if you remember that from a couple weeks ago. So this is our true given. Okay, I'll just write true given for now, but it's short for given premise. Okay, here's our true given. And then after that, right, after that is the second part, is what we got to do next. We got to write a series of formal statements showing that if one thing, if I have a true given here, then I'm going to get another fact proven at the end. Then something else necessarily follows from it. Okay, that second thing right there is called the conclusion. Okay, it's the thing after the event, right? If 3x plus 2 equals 20, then x equals 6. So this is the conclusion. And right, what we want to show is that it's also true, right? That is our goal, is that we also want to show that it's true. Do we know it's true yet? No. So I'll put a question mark right here, but we want to show that it's true. It's hard to read that I said true here, okay? So what I wanted to show you on this slide mainly is this, and I know I'm saying a lot on this here, but I just want to get it out, and as you can tell, I like this. I enjoy doing this here, is that you put your math over here, you put your reasons over here, but you can also read this, right? So the reason why this works as a proof here is because what we're really doing is we're rewriting if-then statements, okay? So listen to me here. Your given starts as, that's your if statement. So if, next to our given, okay, if 3x plus 2 equals 20, okay, the reason why we know if 3x plus 2 equals 20 is because, okay, so I'm going to put because right here, or B/C for because. If 3x plus 2 equals 20, because it's given to us. And then at statement 2, I'm going to write then. Then we can conclude, okay, then we conclude that 3x has to equal 18. If 3x plus 2 equals 20, because it's given to us, then we conclude that 3x equals 18. But hey, I made a statement right there. What's my justification for that? And that is because of the substitution property of equality. So if 3x plus 2 equals 20 because it's given to us, then 3x equals 18 because of the subtraction property of equality. And then, right, because I know if now we've proven that 3x equals 18, then I would know that x would also have to equal 6 because of the division property of equality. So I just wanted to point that out, that here's how you can double check your logic makes sense at the end. You don't have to write these if-then stuffs here because this is just how your proof is written. If 3x plus 2 equals 20 because it's given to us, then 3x equals 18 because of the subtraction property of equality, and therefore, right, therefore x would have to equal 6 because of the division property of equality. Those words aren't written there, if and then, but it's how it flows, right? We know that we have a true proof. Let's get through 2 more examples, guys. You just want to get examples. You want to move on with your lives. That's why I'm trying to do this quickly, even though I'm telling you a whole bunch of stuff. It's the right thing to do to tell you this stuff right now, though. Let's prove a new fact. Given this, okay, we got a new equation, my friends, new equation. We want to prove this, x equals 2. Hopefully it's the right equation this time. Hopefully I didn't screw things up here. All right, gonna go ahead and collapse this, move this up here. Given is this, prove that. So this is our given premise. We know that this is true because it's given to us. This is what our problem is. So that's going to be our first statement. First step, put the given in there, right? That's almost always what you're going to do when you prove stuff. Your first statement is going to be your given. And the reason, right? The reason why I'm saying if this is because that's our given premise. If 5x plus 4 equals x plus 12, then what can we say? Okay, so it might have been a little while since you've done Algebra 1. That's fine. So I'm going to tell you how I would kind of solve this. But my next statement is, well, what I usually recommend to algebra students is I got x's actually on both sides of the equation. So what I would do is I would move x to being only on one side of the equation. Let's collect our variables to one side of the equation. So let's see if we have a statement down here that has that with x only being on one side of the equation. I think it's this one. I think that would be the next thing we would say next. So we have this right here. So I'm allowed, if I know this, I'm allowed to say this because what did I do? I subtracted x from both sides. So I've subtracted x, and x equals x, right? We're allowed to do that because we're subtracting equal things from both sides of the equation. So that is the subtraction property of equality. There we go, subtraction property of equality. Next step, what are we doing? Well, here, 4x plus 4 equals 12. You guys should all know to solve this, even if these folks are still in Algebra 1. Subtract 4 from both sides, and that is the subtraction property of equality. So I got to do this. Then, right, if I now know 4x plus 4 equals 12, then I know that 4x equals 8. Justification, I did it again. I did the subtraction property of equality again here. Okay, last step. Who's got my last step, my friends? How do I solve this? 4x equals 8, right? How do you know the answer? I know you can plug it in, right, guess and check, but no. That's not a rule. What's a rule I can use to justify this? I do what to both sides? I divide both sides by 4. Okay, so I divide 4x equals 8, divide that by 4, divide that by 4. 8 divided by 4 is 2, 4x divided by 4 is x, and we're good to go. And the reason why I know that, division property of equality. And that's it, right? That's how you write an algebraic proof for this here, actually proving that x equals 2 here. Let's keep moving on, folks. You see this here. We're almost up to the end of those slides, and we can be done and move on with our days. Here, just reminders on this. Okay, remember, this is a series of if-then statements. If this, our given premise, and we know it's that a given, that if we can make it a statement, if this, because it's given to us, then 4x plus 4 equals 12 because of the subtraction property of equality. But then also, right, if 4x plus 4 equals 12, then 4x equals 8 because, right, well, again, we use subtraction property of equality because we've subtracted 4 from each side. And the last word you sometimes you'll see in proofs, actually, not your textbook, but other textbooks will do this. They'll actually do therefore. They won't actually like write it out, but sometimes there's actually a symbol for therefore here. Here's actually the symbol for therefore. There's always like a few people who've seen it before. It's 3 dots, right? 3 dots. So sometimes in other textbooks, you put the 3 dots here like in a triangle kind of thing, and it means therefore. Therefore, x equals 2 because we use the division property of equality to get us from step 3 to step 4. Almost there, guys. Almost there. Again, right? Like, get on it. Like, gotta enjoy this math stuff. That's why I'm filming these videos for you. And we get one more fact. All right, here we're going to start with something. It's got a fraction in here. Answer also has a fraction. So anyways, that fraction will be kind of messy here. Let's see if we can tackle this one. Let's get in there. Let's do this. Cool. So let's get rid of it here. All right, anyways, given 3x. So when I write proofs, I just start with the given, guys. You want to do this quickly. You want to get on with your merry lives. You want to get done listening to Mr. Ford talk right here. So we're going to put the given up top here. So if this is true, then I got to prove that that's true. So now, look, I got to use the rules of algebra here. I got to use some rules to simplify this here. First step, what I normally say in this one, or not normally say, what I'd say normally when we have variables on both sides, because notice there's an x here, there's an x over here, is I would collect variables, but not on this one. I'm not going to collect variables because that's kind of messy. Why is that messy? Well, we have a fraction right there. We have a fraction right here. So quick question, there's actually like a step maybe to make your life a little easier when you have problems with fractions, when something's being divided by 2 somewhere in your equation. What can you do to the whole equation to get rid of the fraction, right? To get rid of that denominator that's not 1 in these. What can I do to both sides? I can multiply both sides, okay? So I'm going to put this down here. I can multiply both sides. There's your hint right there. If I multiply both sides by what? What gets rid of that fraction, that negative 1/2? I can multiply both sides by 2, okay? Multiply both sides by 2. So if 3x equals 6 minus a half x, because it's given to us, then we can conclude that 6x equals 12 minus x, because 3x times 2 is 6x, 6 times 2 is 12, and negative a half x times 2 is just negative 1x, right? Negative a half times 2 is negative 1. And here we have negative 1x, so we're good to go, okay? Multiplication property of equality in that one. What am I doing next, guys? What am I doing next? Now I'm going to collect variables, but what's my justification? I want to get my variables over here because I have more of my variables over here. What am I doing to both sides? I am adding x to both sides, plus x to both sides of the equation, and then I get 7x equal to 12 right here, okay? And that is because of the addition property of equality. Okay, we got addition property of equality right here. And then finally, last thing I got to do to solve this one, guys, I think you probably know the last thing here. I'm going to do what to both sides? Divide both sides by 7. Okay, divide both sides by 7. 7 divided by x, sorry, 7x divided by 7 is x. 12 divided by 7 is 12 over 7. Improper fraction, that's fine. You can write your answer as that. You're good to go. You have proven your facts. That's what you were set out to prove. You've done it, and you have your justifications right there. That's it for me, guys. That's it for the kind of lecture, talking you through it. Hopefully you watch this. I think it's a valuable one to watch, even though you might be feeling a little overwhelmed right now. We're going to spend pretty much all week on section 1.4. So that's it for the lecture. I'm going to do maybe one example for you guys of what one of your homework problems will look like tomorrow, right? Tomorrow, Tuesday. So watch out for that video. I might put it at the end of this video too, just so you have it. But a little example of one of the textbook problems looks like. And now that you've got done with this lecture, you got to remember to do your exit ticket. Turn that in before Tuesday, your asynchronous class, and you'll be fine. You'll get credit there. And then you'll do your problems section 1.4 for asynchronous class tomorrow on Tuesday. Thank you very much for watching. Bye. All right. Hey, guys. Here we are over on my notebook over here. I know I haven't said it to many of you guys here, but definitely try to get a graph paper notebook. It's just a lot easier to just keep your proofs organized, and I can tell you that now because we've seen some proofs. Again, your proofs are written in 2 columns, and that's how we'll do it today. So the grids, right, especially with these vertical lines right here, make it a lot easier to organize your 2-column proofs, and also make it easier to draw shapes here. So I wanted to call that out. Your homework on Tuesday is going to be classwork homework. It's just going to be this. It's going to be page 20, numbers 1 through 6. Those are the written exercises. So the first 6 written exercises, all you got to do on Tuesday. And that's really all I got to do is turn in. We're going to do number 5 together as well today. So got my textbook over here. I'm ready to go. I got my notebook over here. I'm ready to go. I got my grid paper to help keep myself organized. Over here in the textbook, so this is what we're going to spend pretty much all week on, section 1.4, properties from algebra. We're going to move this towards geometry in Wednesday and get more practice on Friday. But I just want to call out that we've entered in now a new mini section. Again, we did the self-test last week on Friday because we finished the first mini section on the points, lines, and planes, the undefined terms and related definitions. This is the new mini section we're on right now, Introduction to Proof. So you can read the objectives kind of on your own time. And really, we just introduced proofs to you just a few minutes ago in our first video here for section 1.4. So anyways, properties from algebra, just to reiterate in the video too, you should have taken notes on all this. I put another reminder here, right, in the book right here. Guys, it's written right here. This is some of the most valuable rules that you have in the entire book. So you got to make sure you've written all of this down, and so you can begin trying to determine what this means. Addition property of equality, multiplication property of equality. What the heck the transitive property is here. Did I explain it well? I don't know if I did. Normally you need to hear the transitive property a few times and practice it a few times before you feel like you really get it. So reflexive property. So here, make sure you have all 8 of these written down. I say 8 because, hey, I didn't talk about the symmetric property with you. The symmetric property really doesn't matter. It doesn't come up in this textbook really much at all. But anyways, in case you're curious, the symmetric property, check it out. If A equals B, then B equals A. Right? That basically means if 2x equals 4x over 2, then 4x over 2 equals 2x. Anyways, that was probably too complicated. The whole idea is if something equals another thing, then that other thing equals the original something. Right? If 1 equals 2, then 2 equals 1, right? Or number 1 equals number 2, then number 2 equals number 1, right? So it's pretty obvious here that it doesn't matter what you write on the left and what you write on the right. You can flip-flop and it's totally fine. So that's symmetric. Anyways, that won't really be in the geometry stuff, but reflexive property definitely is. Transitive property definitely is. We're not going to use those 2 today, okay? So heads up here, when you're solving equations, you don't really use reflexive and transitive all that often. These will be more important when we get to geometry here. Okay, anyways, getting into it, we got to do number 5 as an example, and then you'll just have 5 problems for homework beyond that. So that's the reason why I want to do this as an example. So maybe you read a bit below it here. You read page 17 because they're going to talk about an example down here as well. But beyond that, once you get to the geometry type stuff, this is the kind of stuff I'm going to review with you guys on Wednesday. So don't really worry about page 18 yet, or page 19 for that matter. You're welcome to read it if you want to, but you don't have to. So let's go ahead and find the problems you'll be doing. Okay, you're going to be doing these problems today or tomorrow, right? If you're watching this on Monday, these are your written exercises. So you're going to do problems 1 through 6. This is your classwork homework, asynchronous classwork and homework. Shouldn't take you very long. You hopefully can get it done in the 25-minute asynchronous class. But the one I'm going to do with you guys today here is number 5. Written exercises, it says justify each step. Justify each step. So they've written in a lot more here than I wanted them to write in here because I actually want to write a proof here. What they've written here, these are basically statements of a proof because remember, in a proof, and I'm going to write this down here the way that I want you to do it, I want you to do this as a 2-column proof. So get used to this here, 2 columns. So right, horizontal line and a vertical line. We got it set up here. Left side of a proof. Do you guys remember what the left side goes here? Well, they're written down here. These are where your math or geometry statements go. Okay, so you can make statements using numbers, but the thing that your teachers probably pushed you on in the past, which is you can't just say what the answer is, right? How one thing gets to another thing, because you got to say why. You got to say why, and the why here is the reason you have to back it up. And remember, Euclid's logic was airtight, right? Airtight, as Salcon said, airtight, right? As Mr. Fortin's saying right now, and I think Lincoln thought it was airtight too, and that's the reason why he found inspiration for it in terms of becoming a lawyer here. So he used reasons, right? We're going to use reasons this year to make sure our logic is airtight. So I would set it up here as a 2-column proof. All right, here, this is our given. So this is the original equation we start with. That must be our given premise of this problem here. So I'll write this out here too. Given 2 over 3b equals 8 minus 2b. Then we want to prove this, right? We want to prove that b equals 3. So basically what we want to do is we want to put together the work here to basically know that if we're given this, then we would know that that's true. Now that's true, so that in the future, if we have an equation like this, we can just say, oh, b equals 3. We got that. We've done it before. We've proven it before. I doubt you'll have this exact equation ever again in your math career, but hey, you might as well prove the answer with me right now. Good old Mr. Forden, as we have here. Okay, get out of my way. Get out of my way, pen. Out of my way. All right, so let's do this here. The first step to a proof is what? Oh, my first statement. And what is my first statement? Well, that's going to be what we're starting with. My given premise. 2/3 b equals 8 minus 2b. And the reason why I know that is true, well, it was given to us. It was a true given premise. They're not lying to us. They're giving an equation to us that they know is true. And then we got to work with it. They actually give you the statements here in these problems. So what I would do is just fill out maybe all your statements here. This is going to be, let's see, statement 1, 2, 3, 4, 5. This is a 5-step proof. 4 and 5, you can layer it out here. And for every statement, there's going to be a reason. Any statement you make in math, you got to back up. Okay, and that's what you're picking up this year is some of the most important reasons that we have. Some have been around for thousands of years. Other ones have been discovered more recently than that. And we'll talk about some of the ones that have been discovered more recently here. Okay, so this is given. So we start with this. We're getting this into the next step. Ooh, what did we do? What happened? How did our equation change? What happens here? Well, we noticed here that we had 3 as a denominator, okay? So maybe I'll actually show some of the algebra here on this one here. So we had 3 as a denominator. So it looks like in order to get rid of 3 as a denominator, probably what I would have done, honestly, was multiply by 3 over 2. But anyways, just multiply by whatever the denominator is here. So it looks like we multiply both sides by 3. Okay, in order to make this, get rid of the fraction, right? Get rid of the fraction. If you see a fraction, you might as well multiply both sides by the denominator, and that's going to fraction bust. We'll get rid of the fraction right here. 3 times 2 over 3, right? The 3's would cancel. We're left with just 2b here, equal to 3 times by the quantity 8 minus 2b. And they didn't actually distribute yet, but I think that's going to be the next step here. Okay, so step 2, the reason why I know I can start with my given premise like this, and then I can write 2b equals 3 times the quantity 8 minus b. Well, how can I justify that? What did I do to both sides? Right? What did I do? I multiplied both sides by 3. So this is the multiplication property of equality. Note, you can't just write multiplication. So you got to write multiplication prop of equality. The reason why you can't write multiplication is because it's not specific enough. You're using you're flexing a property of equality, meaning if you have equality, statements of equality, if you multiply both sides by the same thing, equality is preserved. If you just wrote multiplication right there, that's vague. You're just saying, hey, I just multiplied something. You know, I'm like, cool. What did you multiply? Did you multiply an inequality? Did you multiply just an expression? No, you're multiplying equations by both sides by the same amount. That's the multiplication property of equality. All right, next step right here. We got 2b equaling 24 minus 6b. This is something I didn't cover earlier in the video because it's not that important here, but I wanted to call it out. Again, I didn't want to distract you right now. What's the reason here? If you've done Algebra 1, you should know what this reason is, okay? How I can go here from 2b. So 2b didn't change. On the left side didn't change. My right side got rewritten though. How did my right side get rewritten? What exactly happened? Well, I hear somebody shouting it out. You distributed. So remember this? Parentheses means multiply, and this is the distributive property of multiplication over addition or subtraction. So here, these individual terms both got multiplied by 3. 3 times 8 is 24. 3 times negative 2b is negative 6b. So our justification, how our equation changed, is that we distributed. So I'm going to write down here distributive property of equality. Again, it's kind of annoying the book does this because it's not important in geometry, but you are going to write it on this homework here. Distributive prop of equality. And check it out here. This is another thing that in my talk earlier I skipped over because it's not important at all, but your book just wants you to practice it. Maybe they think you just learned the distributive property, but they have listed it down here. So properties of equality and other properties from algebra, such as this distributive property here, can be used to justify steps when you're solving an equation. So in the reading, they do talk about the distributive property. So they'll come up in this problem set. Will they come up in future geometry problem sets? No, not really, unless they're just practicing solving algebra for whatever reason. But anyways, so just didn't want to be like, where did that come from? I didn't teach that here. This one here, I'm gonna write here not important next to it because it's not important. Not important that you really get that. Anyways, all right, so we got to finish massaging this equation so we can actually prove our fact that b's got to equal 3. What am I doing to both sides? Well, I gotta collect my variables. So it looks like I gotta add 6b to both sides of the equation right here. And so I'll do that, shall we? So let's add 6b here, and let's add 6b here. And I'm gonna get what? I'm gonna get 8b on the left side equal to 24. The reason why I can make the statement 8b equals 24 is why? Why can I make? Well, I knew statement 3, 2b equals 24 minus 6b was true because I proved it so far. Well, what did I do to both sides? I added to both sides the same equal amounts to both sides here. And what property is that called? You guessed it, the addition property of equality. All right, we're good to go, almost good to go. What's my last step, guys? What's my last step? Yes, I got to establish that b equals 3. Why do I know that b equals 3? Well, I knew that if 8b equaled 24, and I know it is, I've proven that so far. So if 8b equals 24, what would follow from that is that then b would have to equal 3 because we simply divided both sides. So last step is the division property of equality. And there we have it. We have done number 5. Number 5 is good to go. We've proven it here. Rewatch this as an example if you're confused, and then hopefully you understand it and you can try the other 5 problems. Make sure you do all 6 of them, right? So make sure you have this in your homework, but your Tuesday homework is this, numbers 1 through 6. And if you're watching this on Monday, go ahead and do that exit ticket on Desmos, and then worry about this tomorrow when you're doing Tuesday's asynchronous class. Thanks so much, guys. Email me if you have any questions. Bye.